So last time we were talking about free fall a little bit, and we sort of got into the idea of drag and stuff like that. And here's just a couple of pictures from like a wind tunnel where they take objects and they put them into a special tunnel full of wind with special smoke generators, and the smoke then goes over the object and see how well the air actually flows over the object. And here we got it's actually a golf ball actually, and you can see behind the golf ball, the air is coming from this way, and you can actually see behind the golf ball how disrupted the air is. So we were talking about the vacuum yesterday, and of course we got the impact in the front of the ball, and then we've got that vacuum created behind it, and that low pressure back here. We've got low pressure back here is actually going to hold back the ball. So those two things really coming together really makes it not very aerodynamic, and it doesn't really work that well. Where the second shape here, this is what's called an aerofoil shape, aerofoil. And this is one of the ideal nice shapes where this is what's used for like plane wings and propellers and things like that, which are very aerodynamic. And the air is able to come here, it splits up very nicely, but then also is allowed to come together very, very nicely on the other side, really reducing and limiting the amount of vacuum behind here, unlike something like a ball. So this is the idea behind drag and that type of stuff. And I showed you the expression, the force of drag is 0.5 CD rho A V squared. Last time, the 0.5, that's for both of them, but coefficient of drag, this ball has a much higher coefficient of drag than this aerofoil does, because the aerofoil lets the air travel much nicer over it. So the general function of the shape is a lot better for the aerofoil than it is for the ball. And something really boxy, like a semi-truck, would be really, really, really bad. The density would actually be the density of air. That's the same for both of them. The impact area for them, it totally depends. But the biggest difference between the two is definitely the coefficient of drag. So you try and make things as aerodynamic as you possibly can, and depending how you position object, structure an object, their coefficient of drag can change quite a bit. So even for example, like a person who is, skydiving, you've got a person skydiving, and they're positioned like this compared to somebody who is maybe in a diving position. This person here will have a lot more drag. Their coefficient of drag is probably around 1.2, 1.3, 1.4, and this person's coefficient of drag is probably around 1, just because they're so much more aerodynamically placed. Of course, their impact areas will also be different as well, but their coefficient of drag, just by changing the position of the object, can significantly change the coefficient of drag for something. Okay, so that's the basic idea behind what we're going to look at. I'm just going to practice a little bit of drag calculations. It's really, really simple, not using this, but just the idea, sort of like friction. We're talking about how this is sort of like friction a little bit, and sort of show you how this works. Okay, so let's just take something really, really simple. We're talking about skydivers and that type of stuff before. So let's say we actually have a skydiver. And we'll gotta give him his little pack here, something like that. So here is our skydiver falling. I'll give him another eye. And let's say we have a 85 kilogram skydiver, and they're falling along, and they're going down, and they are, let's see, well, let's just do something nice and simple. Let's say there's 150 newtons of drag on them. Okay, and we want to know what is their acceleration. Now we know it's not 9.81 because there's drag. If there's no drag and it was literally simple, it would just be 9.81. But now we can actually look at this a little bit differently and incorporate drag the exact same way you guys have worked with friction. So first of all, I'm going to look at my, how much is trying to move them. So if I look at what's trying to actually move him, of course, that's the force of gravity. So that's just his mg. So if I do his mg, the same way you guys have done before, there's no difference between this when you guys are calculating when you're doing basic dynamics. We've got the 85, we've got the 9.81. We'll round off a little bit. We got about 834 newtons trying to pull him down. So we got 834 newtons are trying to pull him down. But I've also got drag. And apparently I've got 150 newtons of drag. And then 150 is trying to slow him down, so it's going up. So all I have to do is just subtract the two. Okay, I've got 834 trying to go down, I got 850 going up. So my net force would just be the 834 pulling him down, take away 150, so all I have to do is subtract the two, and I've got a net force of around 684 newtons. And once I've got his net force, that's easy to find acceleration. That'd be net force divided by his mass. So I got the 85, so let's divide that by the 85, and we got an acceleration of about 8.0 meters per second squared, so less than 9.81. Now, of course, this can't be bigger than 9.81. You're not going to accelerate faster than free fall. 9.81 is as high as you're going to get for this type of stuff. But that's how you can calculate the acceleration of somebody falling, incorporating the idea with drag. Okay, so it's relatively simple. It's not that big of a deal. And if you go back to your friction stuff, all you have to do is change the drag word to friction, and it's literally the exact same calculations that you guys were working on weeks ago. Okay, so let's take this out here and just try one more. Get rid of that. Okay, and let's have something else fall. Okay, so let's try another one. Here we have a taco that is falling down. Okay, so let's say our taco is 7.2 kilogram taco, and he's falling, and let's say he's accelerating at 1.6 meters per second squared, and I want to know what is the force of drag on the taco. Now there's a couple ways you can do this, but let's just start simple. I have got his mass, so I can find the force of gravity on the taco. If I calculate the mg for my taco, I can find out how much force is actually pulling him down. And there's about 706 newtons pulling him down. Now I've also got the acceleration, and with acceleration I can calculate my net force, basic F equals ma. So if I've got that 1.6 times 7.2, I've got a net force of around, well, we'll just round off. We got a net force of around 12 newtons. Oh, actually this is 70.6, right? There you go, that's better, 70.6. So I got about 12 newtons of net force. So I've got around 70.6 pulling the taco down, but I'm only getting 12 newtons. Well, if I've got like 71 newtons pulling the taco down, but I'm only actually getting 12, well, where's the rest of my force going? Well, that must be what I'm losing to drag. So if I look at just these two forces, I'm actually missing the difference between the two. And I'll just run that to 71 and be done with it. So 71 and 12, I'm missing 59 newtons. So I'm missing 59 newtons. So I'm missing 59 newtons of force, and this, it must be what is lost to drag, so that must be the force of drag. So I've got like 71 newtons pulling the taco down. I've got like 59 newtons pushing up for drag, which gives me my net force of 12. Yeah, it's just that easy. Again, really similar to your friction calculations. Now, if we sort of like change this a little bit, if we look at it a little differently, if we go back to that expression that I showed you guys before, 0.5 CD rho A V squared, as the taco falls and keeps falling, this will stay the same, this stays the same, this stays the same. All these stay the same except for the V. As he falls, his V keeps on getting bigger and bigger and bigger and bigger. So while the taco is falling, okay, during the actual fall, the FG, that's not going to change. That's constant. But the force of drag actually keeps on getting higher because you keep on going faster. So if you keep on falling and falling and falling, the force of gravity pulling you down stays the same, but the force of drag keeps on getting bigger and bigger and bigger, eventually those two forces will match up. And when this occurs, the net force will be equal to 0. So when this thing keeps on going, so when the force of gravity is equal to the force of drag, like drag has actually gotten big enough to bounce off gravity, your net force is going to be equal to 0, which of course means you've got no acceleration. So this would be then, you had this before, this would be dynamic equilibrium. Okay, so oops, there we go. We got dynamic equilibrium where you have no forces, or sorry, no net force, you got no acceleration, you are moving, so it's dynamic, and it's equilibrium because all the forces are equal and canceling out. Now this is what most people know as terminal velocity. So when things fall, they will keep on speeding up, and speeding up. And as they speed up, the drag keeps on getting bigger while the gravity stays the same, and you will reach terminal velocity. So you're not going to keep on accelerating forever. And different things, depending on their shape and their mass and their contact area and their coefficient drag, different things have different terminal velocities. But you can't just keep accelerating forever. So it doesn't really take too long for a skydiver. They fall for a few seconds. They will reach their terminal velocity, and they will just travel at a constant speed. They'll be in dynamic equilibrium as they keep on going down until they pull their chute, and then the drag is actually increased a lot, which actually then slows them down. But that's the idea behind terminal velocity, where the drag actually matches up or equals the force of gravity, and your net force is going to be 0.